Stripping down science. The Naked Scientists.
Hello, it's Sunday, October the 3rd. Welcome to The Naked Scientists. I'm Chris Smith, and this week we're taking on your science questions, including finding out what is the hardest bone in the body to break. I suspect some people have had a go at breaking every single one of theirs. Maybe we'll find out. Also, where do magnets get their energy from? And what causes the bright patterns that you see when you rub your eyes? Also here on the show this week is the king of kitchen science, and that's Dave Ansell. Hello, Dave.
Hi there.
We'll be talking more to Dave in a second. But first, our naked archaeologist, Diana O'Carroll. Hello, Diana.
Yes, hello. And also this week, news of superior solar cells, how the brain decides which hand to use, and a new way to bust drug traffickers.
And I've got a slightly squidgy kitchen science experiment for you to try. You just need yourself and not too dry a mouth.
I'm intrigued. Thank you, Dave. If you've got a question for us that you'd like answered, send your emails to chris@thenakedscientists.com. You can tweet us at Naked Scientists, or you can scribble on our Facebook page. It's the Facebook page of the same name, Naked Scientists.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
It's The Naked Scientists with Chris Smith, Dave Ansell and Diana O'Carroll. And let's kick off, as we always do, with a look at what's hot in the world of science this week. Dave, what have you got for us first?
Well, engineers have built the first flapless aircraft. Ever since the Wright brothers first took to the air, aircraft have been controlled by moving surfaces which deflect the air, and therefore the aircraft gets deflected in the other direction. You can control the plane. And in most cases, this is a tested technology and it works well. But moving surfaces can be a maintenance headache, they create lots of noise, and in military aircraft they can ruin your carefully crafted stealthy shape. Now, researchers from BAE Systems and Cranfield and Manchester universities have flown the first aircraft without moving surfaces at all. Instead, they've been controlling it using something called the Coanda effect. This is the tendency of a stream of fluid to stick to a curved surface.
In this case, fluid being air.
Yeah, air's a fluid. And you've probably seen it if you've ever held a spoon up to a little stream of water from a tap. The water tends to stick to the back of the spoon and it curves around and deflects the air. It's actually a lot of the reason why aeroplanes fly. At the point at which the air detaches from the spoon or the curved surface is very, very sensitive to minor deviations. So what they've been doing is blowing air from the engine into that stream and altering the way, whether it stays attached for longer, in which case the air goes downwards, or becomes detached earlier, in which case the air goes higher than it would have done otherwise.
So you're giving the plane a push using moving air rather than a moving part, but then surely there's got to be a moving part to make the engine duct more air onto that surface, isn't there? So aren't you just moving the problem off of the wing and internally somewhere?
But you're changing it from a very large moving part, which needs big servos and things to move. You actually need very little air to cause these deflections, so they can do it right in the heart of the aircraft where it's nice and protected. They can just make small deflections to it.
And this is working, is it?
They've got it working. They've got a plane. I've seen a video of it. It's a bit slightly hyper. It looks like not entirely smooth control, but it works. It'll probably appear in military aircraft first, as most of these things do. And probably, I don't know whether you'll ever see it in airliners, because many of the advantages aren't a big advantage for airliners. But there are related technologies to this which can reduce the noise of aircraft taking off and landing, and which might be much more practical and we might be seeing in the future.
So the bottom line is you could scale this up to a jumbo. There's no reason why just these little test aircraft are going to be restricted to that sort of size. You could use this on a commercial scale.
Yeah, the only big issue is that at the moment you need something to blow the air, and then that's another point of failure, which might be slightly worrying if you're building an airliner.
Well, I guess it all comes down to testing. On the other hand, Diana?
Well, actually, on the other hand, indeed, researchers writing in the journal PNAS this week have come a little bit closer to understanding how the brain chooses which hand to use for any particular action. And they think it comes down to a sort of mental competition between the hands. Flavio Oliveira and his team from the US and Belgium collected together a group of right-handed people and instructed them to reach for images placed on a table. The participants could use either hand to pick the images up, and these images were in different places on the table. So while this was happening, the researchers applied transcranial magnetic stimulation, or TMS, to the brains of the participants. Sounds scary, but what it does is to temporarily disrupt brain activity in the subject subject's left or right posterior parietal cortex. And as the name suggests, it's at the back of the brain, and it's important for planning movements or thinking about 3D space around you. When TMS was applied to the left side, the right-handed participants tended not to use their right hands as much as they would normally, but applying TMS to the right side of the brain produced no change at all. And of course, the left side of the brain is usually involved in controlling the right side of the body and vice versa, so you might expect to see this in right-handed people.
So what do they actually think is going on? Are we saying here that there's not just this bias to use one hand if you're right-handed or the other hand if you're left-handed? There is actually a section of the brain which is actively encoding which hand to use based on the task at hand. Excuse the pun.
Yeah, well, the researchers think that what's actually going on is some kind of decision-making process in the brain where it's coming up with a series of sort of intentions of how to pick up this item, and then it decides on the best one. So it will probably decide on your right hand if you're right-handed.
I guess another interesting spin-off of this will be to look at people who have strokes and brain injuries, because obviously if you damage that area of the brain, what does this do to a person's ability to make that choice, and how does that affect their rehabilitation? Do they mention that at all in the paper?
No, but I think another thing that would be really interesting would be people who think they're left-handed, but because of various pressures of society, they've had to use their right hand for things, and it would be interesting to see if the same effect happened to them.
Indeed it would. Thank you, Diana. Well, also in the news this week, astronomers at the University of California at Santa Cruz and also from the Carnegie Institution of Washington have announced the discovery of an Earth-like planet, but it's outside our own solar system. And it's thought that liquid water, as well as an atmosphere, could exist on that planet's surface, which would make it, potentially, the first habitable exoplanet. And joining us from the University of California at Santa Cruz to tell us more about the discovery is one of the co-authors of the paper, Stephen Vogt. He is the Professor of Astronomy and Astrophysics. Hello, Stephen.
Hello, Chris.
Thank you for joining us on The Naked Scientist. The first question, I think, probably to kick off with is, where is this planet?
This is in the constellation of Libra. It's about 20 light years away, so it's one of the nearest stars. And it's a pretty exciting star to be looking at.
What's the name of the star?
The star is called Gliese 581G. That's after a catalog of nearby stars by a man named Gliese, basically, so it's number 581 in that catalog.
And how did you actually spot the planet, or planets, because this isn't the first planet that's been spotted around that star?
That's right. A number of groups have been observing many of the nearby stars for many years. The Swiss group from Geneva has already detected 4 planets around this system over the last 4 or 5 years using about 4 years' worth of data, and we've now found 2 more in the system.
So talk us through the experimental methods you use, because even though something is relatively close, 20 light years, it's still far enough away that conventional telescopes are going to find that tricky. So how do you do the study?
The study is done by measuring the velocity of the star. We take a spectrum of the star and measure the shifts, the Doppler shifts of the lines. Every night we get one data point, basically, so we have hundreds of nights of observations on there. And we're basically measuring how the planet tugs on the star. And this particular Earth-like planet tugs on the star at a level of about 1 meter a second, so it makes the star sort of stroll back and forth with a period of about 37 days.
So because the planets in orbit are making the host star wobble a bit, you can pick up that wobble because it makes the light which is coming to us from that star get a bit stretched out or shrunk a bit, and we can pick that up. That tells you that there's something pulling on the star, but how do you resolve individual planets? Because as you've already mentioned, there are a number of planets going around that star.
That's right. There's 6 of them now, so each one pulls with its own period, and these are strictly periodic Keplerian motions. And we fit these out using very sophisticated computer programs, and we strip them out one at a time. With each new planet, once we remove it from the system, then we look at the residuals and look for periodicity in the residuals, and we work our way down through the system one at a time. So the overall dance that is done with 6 planets is quite complex, but we have mathematical techniques to follow that.
So presumably you have worked out the only possible solution to all these different wobbles is if you've got a planet which you say is Earth-like, it's in what's called the habitable zone around that star. So what can you tell about that planet?
Well, what we know about it is that we know its mass. We know we have a lower and an upper limit to its mass. It's about 3 to 4 times as massive as the Earth. We know what it's made out of. If it was made out of styrofoam or marshmallow cream, it would be one temperature and one size. We know it's made out of the sort of stuff that planets are made out of, mostly iron and silicates, things like that. So we have a pretty good estimate of what its radius would be from very detailed models. And that turns out to be about 20 to 50% bigger than the Earth, and spherical. It would be a spherical ball. It wouldn't look like a donut or something like that. So now we know its gravity, basically. We know its surface gravity, and we know how effectively it can hold on to its atmosphere. And it turns out to have about an Earth gravity, maybe a little bit more. So if you stood on a scale on the surface of that planet, you wouldn't be too shocked. Your weight would be about the same as you weigh on the Earth. A
relief for many people. What about the conditions on the planet? Can you infer anything about what it would be like if you were to go there?
Yes, actually, we know a fair amount about that. We know that the planet is tightly locked to its star, so it keeps one face towards its star all the time, just the same way that the moon keeps its same face towards the Earth all the time. And that would mean that it would have a hot side and a cold side, and then a whole bunch of temperatures, a range of temperatures in between. So the area between the bright and the darkness, what we call the terminator, would be the most comfortable. And much of that would be shirt-sleeve weather. You could just stand outside, and there'd be mild winds, mild breezes, but it would be temperatures of basically about 20 to 40 degrees Celsius. It would be quite cool, quite nice. And presuming that it had an atmosphere, there would be probably liquid water on the surface, either in vast quantities or in small quantities. So it would be quite a pleasant place to be.
Which is encouraging. And just to finish off, given that you found this relatively hospitable-sounding place relatively easily, what does this tell us about the prospects of finding more like it elsewhere in the Milky Way? Because our own galaxy's got, 200 billion stars in it?
Yes, yeah, and that to me, that's one of the most interesting things of this discovery, is that it occurred too quickly and too nearby. We shouldn't have found it that soon. And that means one of two things. Either we've been really lucky and we won't find another one again for a long, long time, or there's a lot of them out there. And I prefer the second hypothesis, that there are a lot of them out there. And if you work out the statistics of the numbers from our incompleteness of our surveys, you find that probably 10 to 20% of stars have planets like this. And that means tens of billions of these places in our own galaxy. And that's quite exciting.
It certainly is an intriguing thought. Thank you very much, Stephen, for joining us. Stephen Vogt from the University of California at Santa Cruz. Dave.
Now, scientists have demonstrated a new way of improving the efficiency of solar cells. At the moment, solar power is significantly more expensive than fossil fuels, and there's tens of thousands of researchers trying to reverse this relationship. However, this isn't really just a case of making the solar cells themselves cheaper, because even now in the Western world, half of the cost of installing solar panels is in the installation. So the best way of making electricity cheaper is to get more electricity per square metre of panels. The problem is that different colours of light have different energies, and light split up into little tiny particles called photons, and each photon in a normal cell can only produce one electron. And the solar cell is designed around a single energy called the band gap. This means it can't absorb light with a lower energy than this. Any extra energy a light photon might have is wasted as heat.
So does that mean then, sorry to cut in, Dave, does that mean then that if you optimise your panel to, say, see green light, anything that's at the red or the blue is much harder to get the energy out because the panel isn't optimised around that particular wavelength of light?
That's right. You wouldn't be able to absorb the red at all, and the blue light, any extra energy the photon had above the green, it wouldn't be able to absorb at all. So they tend to probably build them optimised somewhere around the yellow in the spectrum, which means you're wasting lots of infrared and lots of energy from the blue. Now, one solution to this problem would be to find a material that would push 2 electrons around the circuit if the energy of the photon was twice the band gap. This would mean that you could make the band gap a lower energy, so you could absorb more colours of photons in the first place, and the really high energy photons you'd get twice the energy out of, twice as many electrons out of. This effect has been observed in solid lumps of semiconductor, but is very inefficient, and you need 3 or 4 times the energy to produce 2 electrons. Now, Justin Sambar and colleagues have been investigating this property in quantum dots. These are tiny lumps of material, in this case lead sulfide, which is so small that their energy levels start to look more like an atom than a bulk material. But they're an atom whose properties you can engineer. They're built structures of these lead sulfide nanodots attached to titanium dioxide semiconductors. And although these absorb a tiny proportion of the light hitting them at the moment, because they're incredibly thin, when they do absorb them, when they increase the energy of the photons to be more than twice the band gap, they almost see a doubling in the current produced. So they're producing multiple electrons per photon, although it's really not a practical cell at the moment. Hopefully in a few years' time they'll be able to get this into practical cells and get a much higher efficiency out.
And the theoretical efficiency, if you could do this, would be?
I think it's sort of in the 60%.
Which is incredible, isn't it? Much better.
I mean, probably you wouldn't get there, but certainly you get a lot closer.
We're talking of light. There's also an interesting paper out this week which uses a trick of the light to potentially give people who are trafficking illegal drugs a run for their money. It's by a researcher called Tasneem Munshi, who's a researcher at the University of Bradford. And she's got a paper, it's published in the journal Drug Testing and Analysis this week. And what they've done is to use the technique Raman spectroscopy in order to spot when someone has dissolved cocaine inside rum. Because what drug traffickers are now doing to avoid sending packages of things which are easy for customs officers to spot and easy for them to analyse, they've taken to dissolving things like cocaine at very high concentrations inside things like drinks. And this means that the customs officers would potentially have to open a suspect bottle, therefore destroying it in the course of opening it to test it if they were suspicious about it. And that could mean that a number of completely harmless cargoes could end up being compromised, which makes the customs person's job very difficult. What this group have discovered is that if you shine laser light, and they've actually taken two frequencies, they've used green light and also a longer wavelength of light, because people are often using green bottles to put their rum into, and one of the frequencies they chose was green. What they find is that if you've got very low levels, 6 to 8% of cocaine dissolved in the drink, they can see this blip coming up on the graph, because when any substance interacts with the light of a certain wavelength, the substance and the things dissolved in it and surfaces, bits of paper, everything does this. You get this unique scatter pattern of the light coming back, which is called the Raman spectrum, which is almost like a fingerprint specific to that particular substance, so you can tell what's there. And they've found that they can detect even very low concentrations of cocaine dissolved in rum, in glass bottles, coloured glass bottles, and even in plastic bottles. And they even went as far as to test, rather than just ethanol, they actually tested some brand names, Lamb's, Navy Run, Bacardi, and also Captain Morgan. They all worked, and the point is they tested 6 to 8% solutions of cocaine. The people who are doing this illicitly are actually shipping bottles of rum containing 60% dissolved cocaine by weight. So there should be no problem with picking this up, and it means that you don't have to compromise the cargo if there's absolutely nothing wrong with it, which I think is a wonderful breakthrough.
Distilling the best science. The Naked Scientists.
It's The Naked Scientists. It's Chris Smith, Dave Ansell and Diana O'Carroll. We're going to kick off with some questions in just a second, but Dave, tell us, if you would, first of all, what have you got in mind with this kitchen science this week? What's that all about?
Well, this kitchen science is just ridiculously simple. All you need is a little bit of spit and a couple of fingers. So what I want you to do is get a good blob of spit on your finger. Hold your forefinger and thumb close together so the spit kind of bridges the gap, then stretch out that spit and form a little string. It works better if the string is vertical. Leave it there for sort of 10 or 15 seconds and see if anything interesting happens. You might have to try a few times because it sometimes snaps, but
so you don't, or you do need, you said dry mouth can help.
In experiments I've been doing before this, the behaviour of kind of snotty, kind of mucousy stuff seems to be slightly different than proper spit. So it works better with proper spit. So you can have a go with both.
We'll give it a go. Thank you, Dave. We'll get Diana on it. She's sitting over there ready to maybe have a go at that one. We've got Doug, who's with us on the phone. Hello, Doug.
Hi.
Welcome to The Naked Scientists. What's your question?
Thank you. I wanted to know, when I'm in a dark room and I rub my eyes, why do I see bright lights or vivid color patterns?
Good question. What you're doing when you're squeezing on your eyeball is triggering what's called an entoptic phenomenon. In other words, it's a hallucination, a visual hallucination originating from inside your own eyeball. When you apply pressure to the eyeball, what you're doing is pressing on the retina. And the retina is the extremely complicated, cell-rich, very highly metabolically active structure that turns light waves into brain waves, to put it simply. And when you apply pressure to the retina, two things happen. One, you deform the retina a little bit, and this makes the photoreceptors, which are the specialised cells that pick up photons of light and change their pattern of firing activity in response to them, which is how we see. It makes those cells change their activity. The other thing that pressing on the retina will do is it may affect its ability to pick up oxygen from the blood, because the photoreceptors are right at the back of the eye, close to something called the choroid plexus, and the choroid plexus is a very dense network of blood vessels. In fact, the retina has one of the highest metabolic rates of any tissue in the body. And if you affect the way at which oxygen moves out of the choroid plexus and into the photoreceptors for even a fraction of a second, they start to deliver abnormal firing activity, and you start to see these funny lights. And you might have seen this if you stand up quickly out of the bath when you've had a hot bath. You may have noticed a similar strange wooziness, but also you'll have noticed some perhaps funny lights in front of your eyes. Did you see that?
That's right, yes.
And that's because your blood pressure temporarily dips when you stand up, and you deprive the photoreceptors of their oxygen supply momentarily, and they respond by firing off all these funny blazes of colours. And so it's an entoptic phenomenon secondary to physical deformation of the retina, but also probably because you're affecting the ability of the retina to grab its oxygen supply. Great question, though. Right, Dave, here's one for you. I love this question. Martin Elbin says, from where do magnets obtain their energy? Why don't magnets ever run out of power to attract or repel, for example?
Okay, in order to create a magnet, you've actually got to put some energy in. Certainly a permanent magnet, you've got to rotate all the little atomic magnets inside the piece of metal, the piece of iron. You've got to rotate them all up and line them all up so their magnetic fields all add together. And that takes some energy, and a magnet does have some energy. But for that to keep on going doesn't require any energy. It's a bit like saying, why does the Earth keep attracting us forever? They're just forces which exist forever. The actual magnetism in a piece of iron or in a permanent magnet is actually caused by essentially electrons orbiting in one direction more than in the other. And the electrons are going to keep on orbiting, as far as we know, for billions of years, as far as we know, forever, unless something interrupts them. So the little atomic magnet's going to carry on forever. There's no reason why the magnet shouldn't carry on.
It's basically not burning off any energy to make the field, and it's something interacting with the field that actually makes an effect rather than the other way around. Diana?
But why is it then that some magnets get demagnetized over time?
Okay, the atomic magnets would stay magnetised, but especially if you drop them, you can cause them to realign a bit every time you drop them. If they get very hot, they can get realigned as well. So the atomic magnets are still there, but they're now instead of all pointing in the same direction, they start to become more and more randomly organised, so the overall field gets less and less and less.
Dave, thank you. We've had a question from Chris Wilson, actually in response to the paper we were discussing, Stephen Vogt's paper on the discovery of this new Earth-like planet orbiting a star fairly close to us, actually. And we've got Stephen back to answer this question. Thank you for rejoining us, Stephen, from the University of California at Santa Cruz. Chris Wilson says, having heard about this new Earth-like planet and the fact that it was discovered through looking at wobbles in the sun, how long will it be before we can actually turn optical telescopes on things like this distant planet and actually really see it? Stephen, what do you think?
Well, that will happen fairly quickly. I don't know if it'll be with this particular system, but we're working very hard on what are called extreme adaptive optic systems for our ground-based telescopes that remove the effect of the Earth's atmosphere, or the seeing, as it were, to allow us to look in real close. And so we have a number of projects like that underway that will be used with large telescopes to be able to see in very close. For something like this, which is in so very close, it will probably take a space-based effort where we actually build fleets of telescopes that operate together in space as like a flying interferometer that can then block out the intense light from the star and allow you to see in very closely. And that's probably 10 to 20 years away.
But it's still close enough that in our lifetimes we're actually going to begin to really see places resembling the Earth, but not in our own solar system, which is originally a kind of gobsmacking thought, isn't it?
Yes, this is a long ways away from our solar system, even though it's a very nearby star. It's 20 light years away. What's even more exciting to me is that one could imagine using nuclear pulsed rocket technology, basically take all the world's warheads, nuclear warheads, and load them up into a rocket ship. You could get up to about a tenth of the speed of light in about a month, and at a tenth of the speed of light, you could reach this thing in 200 years and actually, send a cell phone out there and take pictures and send back tweets, so that would be kind of fun to do.
Not if you use my cell phone. The reception's been absolutely terrible. It'd be even worse out there. But Stephen, thank you very much for coming back and answering that for us. Great to have you on the show. Stephen Vogt, who is from the University of California at Santa Cruz. Diana, this one's coming for you. Calvin Stafford says, what is the hardest bone in, he says your body, but I presume he means kind of anyone's body, your body. Which is the hardest bone in the body to break?
OK, well, I reckon it's the petrous part of the temporal bone. And you can find the temporal bone sort of in behind your ear, underneath your ear. And the petrous part of it is this really solid, sort of stony, is what petrous actually means, bit of bone which goes around all your auditory canals. And it's the bit of bone that survives really well in archaeology as well. I mean, you can sort of bash it and it just sort of stays in one piece. But a lot of people say that the femur is also a really hard bone to break because it is quite solid, it is thick, and it's your thigh bone. But I reckon the petrous part is the best contender.
I guess there's two different questions there. One of how strong is the bone, and also how likely is it to get damaged? Your femur might be incredibly strong, but it's also kind of a major structural part of your body, and when you fall off a motorbike, it gets bashed really hard.
Exactly, yeah. It's one of those that you're more likely to injure. The malleus, the incus, and the stapes, the little tiny bones inside your ear, are probably the hardest to break because they're so hard to get to. But if you took them out and gave them a good bashing, they'd break very easily.
Thank you very much, Diana. I will try not to do that. On the subject of what's in the head, hello, Nick.
Hi, Chris.
Where are you calling from?
Boston, Massachusetts, in the U.S.
Ah, the Cambridge, but on the other side of the Atlantic.
That's right.
Possibly.
That's right.
What can we do for you?
Last week you were talking about people who have had half of their brain removed. And I've also read that the brain has a very gelatin-like consistency. So I'm wondering what happens to the extra space in there. Seems like if they were to stop short or shake their head pretty hard, the stuff would sort of ooze all over the place.
Yeah, you're right. In fact, if you look at what brain tissue is like, it is very soft and floppy. It's almost like blancmange, the kind of consistency of fresh brain tissue. And you're right that when someone actually has to have a portion of their brain removed, it would leave a very big space because the volume of an adult human brain is about 1.3 litres, 1,300 centimetres cubed. So it's quite big, and if you removed half of that from your head, then you'd obviously have a space which is about 700 mils of empty space. Now, people did originally worry that there might be a problem with what to do with this empty space inside the head of someone who's had half the brain removed, and let's just revise why people might have that done. If you have got some kind of problem, for instance, intractable epilepsy, for which this was performed quite often in the past, relatively speaking, especially in young children, for which the recovery actually is really good. They get back pretty normal life, actually, after having this done. It sounds pretty draconian, but it works very well. What you then end up with is this space in the head, and you've got to fill it with something. Well, people did worry that this would be a problem, but what they discovered in the long term is that, in fact, it fills up with cerebrospinal fluid, the same stuff that bathes the brain and spinal cord anyway, and there doesn't seem to be a major problem. The brain is quite well supported inside the head, and although it is floating in this bath of CSF, cerebrospinal fluid, actually there are various supporting structures which help to hold the brain in one position. And going from front to back, so if you imagine if you had your fingers in the middle of your forehead and you ran your fingers backwards vertically over the top of your head towards the middle of the back of your head, there is a piece of tissue called the falx cerebri, which inside your skull follows a sort of similar course to that, and that holds your brain in and stops it going from side to side. And there at the back of the head is also a structure called the tentorium cerebelli, which is a horizontal piece of tissue which holds the brain vertically. And there's also the main meninges, which go around the brain, and they provide a degree of support as well. So it turns out that there's not a major problem because the kind of movements you would have to make your brain go from side to side would be so severe that you'd probably be damaging yourself quite seriously anyway. So actually, as it turns out, it hasn't really become a major problem for people who have had these hemispherectomies. Does that answer the question?
Yeah, it does. Thank you very much.
It's a pleasure. Thanks for joining us on The Naked Scientist. Dave, I love this question, okay, from Phil. He says, assuming it was possible to create a magnet made of antimatter, would it attract or repel antimatter iron or normal iron? Would you get antimagnetism, or is magnetism the same in an antimatter universe as it is in a matter universe? Brilliant.
It's a wonderful question. Antimatter, basically, the main difference we know about it is it's got the opposite charge, and an anti-electron has got the opposite charge to a normal electron, so a positron's got the opposite charge of a normal electron. And magnetism is all about charge. It's actually a sort of minor alteration, a minor tweak to the normal electric field, which is due to a relativity. So Einstein's special theory of relativity predicts magnetism. It's actually part of the way he worked out the theory in the first place. And so antimatter has got perfectly normal charges. It behaves normally, just in the opposite direction. So an antimatter magnet would behave, as far as I can work out, exactly the same as a normal magnet. So it would attract both antimatter iron and normal iron.
The difference being, of course, if it touched the antimatter.
Completely, yeah, it would get immense amounts of energy released. Although the question which no one actually knows the answer to this, is whether it would be attracted or repelled by gravity. So whether it would fall downwards or upwards, nobody knows. No one's been able to measure that yet.
Diana, here's one for you. Hugh Sinclair is speculating, how do fish gills work?
Well, I think they work a little bit like really efficient lungs. So when a fish opens its mouth, in goes the water, it goes into the gill, and they've got a really thin membrane over which the water flows, and on the other side of the membrane, blood is flowing, and it's flowing in the opposite direction, which means that any oxygen which is dissolved in the water can then go through this membrane into the blood. And they're also really, really finely made, so they've got these things called lamellae, and what happens when a fish is out of water, the reason it can't breathe is that these little structures collapse in on each other, and so it becomes less efficient. There's less surface area exposed to the available oxygen, and they essentially asphyxiate in the air. But that's how.
Because human lungs don't collapse like that, because they have surfactant which reduces the surface tension in the water on the surface of these little tiny air sacs, so they don't collapse. But fish don't have that surfactant, because obviously it'd all be washing away and they don't need it. But that might be important for this week's Kitchen Science, because, Dave, just remind people what you've got people doing.
What I want you to do is get a blob of spit between your thumb and forefinger.
Your own spit, hopefully.
Your own spit, yeah. It would work with somebody else's spit, but it's probably more pleasant to use your own. Get a blob between your thumb and forefinger, and then just pull it apart to about sort of 15 mil, or 10 or 15 mil, till you get a little string between your thumb and forefinger. And then if it survives there for 10 or 15 seconds, you should see something quite interesting.
Malkin Lowestoft had a go. He said, did it 3 times, seemed to tighten, became straighter, and then a tiny globule formed and it moved slightly down. But the effect didn't blow him away, if he's honest.
I'm sorry.
We'll let you off. Now, over the past few weeks, scientists have been carrying out the first geological survey since the 1930s of England's largest lake. That's Lake Windermere. It's up in Cumbria, the Lake District. And Richard Hollingham, who is from the Planet Earth podcast, has been along to find out what's been found.
Windermere Lake Warden, this is survey vessel. White Ribbon, over.
White Ribbon, this is Windermere Lake Warden, go ahead, over.
Good afternoon, sir.
Well, it really is a beautiful day here on Windermere. Around the centre of the lake, you've got the trees above the waterline and the green hills beyond that, and then the mountains. And I'm on board the White Ribbon, which is really a slightly large day boat, if you like, but rather than people with picnics, it's crammed with computer monitors and scientific equipment. And with me is Carol Cotterill from the British Geological Survey. Carol, what are you aiming to do here?
One of the aims that we're looking at is the lake bed itself and the modern day processes that are going on, both the sedimentary processes but also the habitats for the fish, in particular the Arctic char. And we also want to know what's going on beneath the lake bed. So what happened in the past, in particular during the last ice age when the British ice sheet came down this far. So did it leave a series of moraines? How quickly did it retreat? And what we can tell about the glacial processes and any changes to the watershed and the drainage into the lake since that time.
Now we're standing on the aft deck here, but beneath us there's a hole.
Yes, that's actually a moon pool, that's what it's called, and it's quite unusual on a vessel of this size. Normally you find them on much larger drilling or geotechnical ships, but here we decided it was much safer for the equipment if we actually carved a hole in the centre of the boat, and we can now deploy our equipment down through the centre of that so we can keep an eye on it basically, and it's semi-protected.
So if we peer down through this hole, you've got an instrument here suspended beneath the surface of the water. What's that measuring?
It's painting a picture of the seabed using sound. So what we have are 2 sonar heads that are angled opposed to each other, and they send out a number of beams. In total we have 508 beams. So 508 sound waves effectively radiate out, or pings as we call them. And when they hit the seabed, they bounce back off the sediments or anything on the seabed, and then they come back to us and we hear their returns. And from the time it takes for the sound ping to bounce down and come back to us, we can then calculate the depth that is.
Now, if we go inside, I think we can see some of the results as they come in. Let's just follow the cable from the instrument into the cabin here, and here's Nick Smart, and you've got 2 large computer monitors in front of you with these very pretty colour patterns in 3 dimensions, but that's what we're looking at now, is that right?
It's directly what's below the boat. We're running along the edge of a contour at the moment. You can see the change in depth, which is illustrated by the difference in colours. The red's showing the slightly shallower area, and then as it gets deeper off to our left-hand side, it goes to the blue.
And Carol, what have you found so far? I mean, I was quite surprised when I looked at these that there was a bump in the middle of the lake.
Across the central section where the current ferry runs, there's actually a high in the lake bed that comes to only 2 metres water depth. It's very, very shallow in certain parts. And we think that this is a remnant of this glacial past that I mentioned before, and that this could be where there's a more solid bedrock that the glacier or the ice sheet couldn't wear down through.
This is material that the glacier would have dumped there, but it's right across the centre of the lake.
It is right across the centre of the lake, and we've seen it in both the north and the south basin as well, much smaller examples. So material that has come down with the water coming out from underneath the glacier, so you get this sort of outwash of debris that the glacier has ground up as it's been on its journey, and it leaves these big ridges that are called moraines. And there are a number of different types of moraines, and in this lake, from a very preliminary interpretation, we think we've got terminal moraines, which are at the sort of snout or the very edge of the glacier, but also a series of digear moraines that build up underneath the glacier.
What's the point of doing a study like this?
It's trying to understand the history and how the lake has evolved, how it might evolve in the future, how the species that live within this lake work with this habitat. Are there certain areas that they prefer to spawn or to feed? Is there the stratification that we find in the lake from temperature, so the top getting much warmer and the bottom quite cooler? Does that have an impact on the species? So it's a whole number of different things.
You're also looking for a monster here.
Yes. When we came down and we launched the boat just over a week ago, we were talking to the lake wardens who were helping us and have provided their jetty, and they asked us to look out for Bonessi. Bonessi. Apparently there have been sightings of Bonessi, and I was shown some photographs that one of the wardens took a couple of years ago.
But no sign yet?
No sign, no. Bonessi's been quite elusive so far, and I think she hears us coming and just sort of scurries away to the deeper parts where we're not working.
And they're still hunting for that there monster. That was Carol Cotterill from the British Geological Survey, and she was with Richard Hollingham, and they were aboard White Ribbon, which is the boat surveying Lake Windermere. If you enjoyed that, there are more of Richard's podcasts, as well as some links to his other Planet Earth resources, and they're at thenakedscientist.com/Planet Earth. Now, Rafaela's with us from Norwich. Hello.
Hello. My question today is why, when your tears run down your face, they go slower than water running down your skin?
Yeah, it's an interesting one. It's something I've noticed. I think probably the biggest thing is that if you put droplets of water on your face, they tend to be bigger before they run down. And the thing is with water flowing anywhere is that a big river will flow a lot faster than a small river. So a big droplet of water has much more gravity pulling on it, so a much larger force pulling it down your face. But the forces which slow it down increase much more slowly. So a big drop will run down your face a lot more. It's possible that the droplets are a lot bigger with normal water than tears because there's probably some surfactants in there. Some proteins mean that it can form, the droplet will break up and start running down your face when it's much smaller than normal water.
So to summarise, Dave, is it fair to say then we think that water droplets are going to be larger than teardrops, which are going to be a bit smaller because there are other chemicals in the tears that mean that the water forms smaller droplets with tears. Because they're smaller droplets, they're less heavy, so they get dragged down your face slightly more slowly, so they run more slowly.
That is, I think, what's probably going on.
Added visual effect, because obviously humans rely on crying to show they're very happy or show they're very unhappy. So, yeah. OK, Rafaela, thank you very much. If you'd like to get a question into The Naked Scientist, then you can do so by emailing chris@thenakedscientist.com. You can also tweet @nakedscientists, or you can scribble your questions down on our Facebook page. It's Chris Smith, Dave Ansell and Diana O'Carroll. We're answering your science questions for you this week, and we've got loads of them. Thank you very much. Diana, here's one for you. Justin McGregor says, did dinosaurs and humans ever coexist as the creationists say they did?
That old can of worms. I believe no. This question always reminds me of that film 1 million years BC, the one with Raquel Welch. But dinosaurs are known to have become extinct about 65 million years ago. Humans turned up, well, all sorts of varying dates, but sort of very early humans, maybe 2 million years ago, then more modern humans maybe 200,000 years ago. So no, not much of an overlap at all. In fact, none.
And I was very fortunate, of course, last week when I was in South Africa to be playing around with the remains of a 2 million-year-old ancestor, someone who I almost certainly will share some genes with, and you and Dave. And this is Homo sediba that Professor Lee Berger from South Africa has discovered, this intermediate species of pre-human that sort of spans the gap between Australopithecus, the very, very primitive people-like things, and Homo erectus and Homo habilis, our immediate ancestors. You would be so jealous if you'd seen...
I'm really, 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 really jealous, actually. I wish I could have seen that. It's not fair.
Got a question from Hilary Groom, who has sent this on Facebook. If you go to Naked Scientists on Facebook, you can find us there. She says, where does the intestinal flora originate? How does the intestinal flora develop in a fetus? In other words, this is the bacteria, the bugs that end up living inside our intestines. How do they get there? Where do they come from? And the answer is, Hilary, they come during your first moments of life, because, unpleasant as it sounds, if you're a baby born the normal way, your first taste of life is a mouthful of muck. And it's your mum's muck, and it comes from the vagina, the perineum, and even from your mum's bum, because there are bacteria that live in that area, all over that area, and as the baby comes out, they go all over the baby's face and mouth, and they go then into the baby's intestines, and they take up residence in the baby's gut. And if you look upon it one way, this is the perfect way to make sure that the bugs that the baby gets inside it are ideal for the kind of food it's going to be eating later, because the bugs mum has got are genetically right for her, they're also ideal for the kind of food she eats, and subsequently that's probably going to be the same food that the baby's going to eat when it's weaned. So it makes sense to get those bugs and get them inside the baby, and they then take up the right sorts of numbers and densities over time, and by the time you're about early teenage, the spectrum of bugs that you've got living in you and on you are more unique to you than your own fingerprints, and they stay with you for life till you're about age 60, and then they begin to change a little bit as the immune system begins to weaken slightly, and the spectrum of those bugs can alter. But yes, the spectrum of bugs that you carry is unique to you, and no one else has quite that same spectrum. Even your identical twin, if they have a slightly different diet or environment, they're going to have a slightly different spectrum of bugs. Now, Dave, this one I think is worthy of taking a look at. There's two related questions. Hamira Patel and also Harold Pettus have both asked about electric currents, and what they're asking is there any matter actually flowing when an electric current actually occurs? What's going on?
There is matter flowing. An electric current is a movement of electrons, which are tiny particles. They're very, very light compared to the nuclei of atoms, but they're about a 2,000th of the mass, roughly, give or take. But they still have mass, they are matter, and they're moving around. And what happens in electric current is essentially you've got a conductor where these electrons can move quite easily. You shove some extra electrons in one end using a battery or a generator or something. Electrons repel one another, so that extra density causes all the other electrons to kind of move away a bit. And so you get this sort of wave, essentially you can be think of it as a wave of movement going all the way through to the other end of the wire or whatever. This wave of movement moves at very close to the speed of light, maybe 0.8 of the speed of light. But the actual electrons themselves are only moving at millimetres a second. So the actual movement of electrons is very, very slow, but there is a movement. But the actual signal moves very quickly, because it's a bit like a Newton's cradle, where you hit one end, a ball on one end, and then all the other balls transfer that impact all the way along until the one on the other end flies away far quicker than any of the balls themselves are moving.
Dave, thank you. Diana, help me out. Who was Madame Bovary?
I think it was a 19th century novel about, I think she was a very naughty lady, from what I remember.
Apparently she killed herself as well. Carol King has put on our Facebook page, Madame Bovary drank ink to kill herself. What is in ink that's poisonous? Is it still in ink today? I wonder what she's thinking. Well, I can tell you that ancient inks, and you probably know this as an archaeologist as well, ancient inks were made by crown galls. So crown gall inks were made. You go to oak trees, you find oak apples, these galls which are on the wood of the oak tree, these little blebs, they look like little round spheres, which are made by a parasitic insect that puts some stuff into the side of the oak tree. It puts some genes in, I think, which then makes the tree grow this little bleb. And they end up being very rich in tannin. So people would harvest them, grind them up, and then mix them with iron sulfate, iron 2 sulfate, which would then extract the tannins, and it meant that the ink was very, very dark, very black when it was first written. It's beautiful. The problem is that it's also very acidic still, so it would rot holes in the ancient manuscripts, which is why when you see ancient manuscripts photographed, they always have where the descenders are, the G's and the Y's, where the person paused their pen and then reversed over themselves. There's a bit more ink there, and that means there's a bit more acid there, and the acid goes into the paper and hydrolyses the cellulose in the paper. It makes a hole, and that's why all these ancient manuscripts have got those holes there. So I'd say maybe she just died of iron 2 sulfate poisoning, because I think if you did have a very intense intake of that, maybe, I don't know, I've not come across anyone managing to poison themselves that way, but I think theoretically it could be done. Does anyone know? Tell us if you have any experience of iron poisoning. I'm not sure. Now, this one. Diana, why is skin black in sunny countries and white in colder climates? Asks Jeffrey McGilvery.
Interesting question. A lot of people think that it's due to vitamin D production. So what happens is you get UVB emitted by the sun, and that goes into your skin, and your skin makes vitamin D. So the darker your skin is, the less UVB can penetrate into it, and the less vitamin D you will make. So obviously the further north you are, the paler skin you want, where you're getting less sunlight. Also, dark skin can give you protection against sunburn, so people like me will know very well that you've got to pack on the factor 50 if you go anywhere near the sunlight. But there's also another thing, is that skin tone doesn't vary directly with latitude. It's not a totally uniform variation that, you will get darker people in very, very sunny places and lighter people in less sunny places. And a lot of people have argued that it's actually, there's a huge social part that plays in skin tone. So sexual selection, for example, will determine how pale certain people will be in certain societies.
Because Nina Jablonski, who we had on the programme last year, is that she's professor of anthropology at Penn State University in America, and she has been looking at this whole question and has shown how folic acid, gets degraded by ultraviolet, and if you don't have black skin and you're subject to a lot of ultraviolet, then you have low levels of folate, and it makes you have spina bifida, for example. So black people evolved to be black in order to avoid getting that kind of folate degradation, because I asked her, if you look at the last common ancestor that we and chimpanzees shared, humans and chimps, because chimps have pink skin, what colour was that? And she said almost certainly had pale skin. So when humans evolved, they had to evolve first to have black skin. And then when we moved out of Africa, 155,000 whatever years ago, people then re-evolved to have white skin for exactly the reason she said. It's fascinating, isn't it?
Yeah, that's right. I've heard that too, and that the very early humans were quite hairy, and so this allowed them to have very pale skin, which was covered with nice protective hair.
A few people knocking around in Cambridge like that today. You're listening to The Naked Scientist with Chris Smith, Diana O'Carroll and Dave Ansell, and we're answering your science questions. But before we do any more of that, we have to find out the solution, if that's the right word to use, to Dave's Kitchen Science.
OK, I asked you to get a blob of spit on your finger, hold it between your finger and thumb, so if you want to have a go at this, Diana.
All right then, I'm going to reach around inside my mouth and... Right, yep, I've got
a nice juicy lump of spit.
I think I've got enough.
And you want to stretch it out,
lump of something.
10 or 15, 10 or 15 millimetres.
Yeah, I can't do 10 or 15 centimetres, it's not that good. Yeah.
And is it still just a straight line, or is there something?
We've got a straight line of globules of.
So what you get is it starts off as a straight line, and then after a while, all of a sudden, it suddenly turns into globules.
Yes, it is in little lumps.
So which is kind of actually quite surprising, because you kind of expect a kind of stringy thing like spit to just stay out as a string.
Mine did that quite quickly.
Yes, so. It's sometimes how fast it happens is dependent on kind of how much mucus is in your spit. It's a bit variable. If there's not enough mucus in there, if you drink too much water, as I was testing earlier, it doesn't work at all, and it won't hold a.
Does that mean I'm really mucosal then?
If you've got too much mucus in there, it doesn't seem to actually form the globules at all.
Oh, okay.
But it makes these quite cute, whatever Malcolm thinks, I think they're quite cute little globules.
Lovely.
So what's going on is that there's two effects. The first one is the reason why it's forming these globules, which is related...
Stop wiping your fingers on the desk.
No one will know.
Which is related to the reason why if you have a tap running, slowly the droplets, the stream of water breaks up into droplets. This is due to surface tension. Surface tension is this property because all water molecules are trying to get attracted to other water molecules. So it has the effect that the surface is pulling all the time with the same force. If you've got a very, very curved surface, I mean, so if you think of a lump on the top of a very curved surface, the surface tension is pulling that lump into the blob of water quite strongly because the two forces are in approximately similar direction. If you've got a not very curved surface at all, almost flat, the surface tension is pulling in exactly the opposite direction, so not pulling in at all. So areas with very curved surfaces have got a higher pressure than areas without very curved surfaces. So if you have a stream and one bit gets slightly wider than all the others, it's slightly less curved, which means it's slightly lower pressure, so water flows towards the uncurved bit, so that gets wider and wider and wider and forms a blob. Now, in a stream of water, that's all that happens. It breaks up into droplets. But because your spit has got some mucus in there, it's got some long protein molecules, those can't move nearly as quickly as a liquid, so they get pulled out into a big long string, and as the water flows past them, the string gets thinner and thinner and thinner, so you end up with this string of mucus with little globules along it.
Delightful. Dave, have you got some nice pictures to show us?
There's a beautiful video of this. I took a while getting a beautiful video, and it's on the website at www.thenakedscientist.com/kitchenscience.
And very quickly, a quick question from Roy in Great Eastern, who says, what causes red eye when you take a flash photograph? Well, Roy, as we mentioned earlier, lots and lots of blood at the back of the eye. When you take a photograph, the flash goes into the eye, illuminates the inside of the eyeball, illuminating that bright red, dark, rich red blood. The light then comes back out of the eye towards the camera through the very big open pupil, and the camera picks it up, which is why your eyes look red. And if you have red eye reduction, what that does is to give a little pulse of light first, which causes you to close your pupil, so the amount of light from the flash that can get into the eye in the first place is reduced, and that cuts down the problem. Right, on the subject of good questions, Diana, question of the week.
Yes, indeed. This week, what goes up is in fact going down.
My name is Brenda. When I was on holiday in Barbados, there was a road that seemed to defy the laws of gravity. If you placed a football at the end of the road, which was quite steep downhill, the ball moved up the hill. I thought it was some kind of optical illusion at first, but tried it myself, and the ball did indeed move uphill against gravity. How is this possible?
So what could possibly cause this effect? Amos Storkey has the answer.
From the description, I would hazard a guess that this happened on Morgan Lewis Hill, which is in the St Andrews district of Barbados. In fact, there are quite a few places like this in the world. They're often known by names of the Magnetic Hill or Gravity Hill, and they are basically places where your eyes deceive you into believing a downhill slope is in fact a slope uphill. So what makes us think that down is up? Well, first of all, we expect things like trees, lampposts, buildings, cliffs, and so on to go straight up. If something is almost vertical, the brain may prefer to believe that it is vertical if it can explain the difference by some other means. The thing is that light, wind, and subsidence can affect tree growth and cause trees to slope. Ground movement can also affect things like lampposts or telegraph poles, often in a consistent way. The overall landscape also makes a huge difference. Sloped or obscured horizons and widening roads can give a perspective effect that a road that curves round is actually headed up. A slight downward slope that goes over an edge can easily be interpreted as a summit. Finally, once natural environment starts to look like Gravity Hill, people come along and deliberately add things, like wonky signs to enhance the illusion, and bring in tourists. Well, wouldn't you? The brain sees all this. If there was one sloping tree, your brain would just put it down to a sloping tree. But if there are a number of sloping trees and a non-vertical cliff, and it looks like the road is headed up due to a sloping horizon, that's it. Your brain just says it's too much of a coincidence and interprets it as the road going up instead. And because this is all unconscious processing, there's nothing much you can do about it.
And that was Amos Storkey, who is a lecturer in the School of Informatics in the University of Edinburgh. If parts of the landscape around the road, such as trees, signposts, etc., are at odd angles, these can confuse your brain into thinking up is down. And we had an email from Brian who said that you can see this spectacularly in the Isle of Man in a car. And on the forum, Giza said that there is an electric bray on the A719 near Dunure in Ayrshire, write that down, and his dad used to turn off the engine in the car, put it in neutral, and they'd roll uphill. And Eric A. Taylor got the answer right too. And just peeking over the horizon is next week's question.
Hello, my name is Sally and I'm located in Halifax in Yorkshire. My question is, When there is a new moon in England, is the moon in Australia the same, or because this country is on the other side of the world from us, is the moon either a day earlier or a day later quite full?
Is the moon always doing the same thing on the other side of the world? Let us know what you think by emailing chris@thenakedscientists.com or by writing on the forum, and that's at thenakedscientists.com/forum.
Thank you, Diana. More from Diana O'Carroll as a Question of the Week podcast in its own right. That's on the website nakedscientist.com/QOTW, or look it up on iTunes. Anyway, that's all we've got time for this week. Next week, we'll be finding out how advertisers get under your skin and into your brain as we explore the field of neuromarketing. We'll be finding out just why the appearance of celebrities makes us want something, and also Smita Mandasad has been grocery shopping alongside a consumer psychologist.
One of the things a lot of people will do is we use these shortcuts. Shopping in a supermarket isn't about consciously evaluating all the time. If you did that, I would think your total shop would probably take you a day.
And you can join Smita next week to see just how supermarkets are using shortcuts and hidden messages to influence what goes into your shopping basket. In the meantime, if you have any questions or comments for us, then you can email them to chris@thenakedscientist.com or send us a tweet. It's @nakedscientists. Our thanks go to our contributors this week, Stephen Vogt and also Richard Hollingham, and thank you to our wonderful production team, Sarah Caster-Perry, Mira Senthillingham, Diana O'Carroll, Dave Ansell, and I'm Chris Smith. Until next time, goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council, and UK FAST. For more information, look us up online at thenakedscientists.com.